we're ready to start looking at integration. In integration, our real question is, how much is there? What's the total? And we've done integration before, so we should feel pretty good about our ability to do integration in one variable. So as we move to multivariable, you might say, well, what do we do? Now, when we talked about derivatives, we said, hey, we could differentiate one variable at a time. Maybe we can integrate one variable at a time. And the answer is, yes, that's exactly what we want to do. Aha, good. Now, of course, we got to get there. We got to figure out what's going on. But you'll see, look, multivariable calculus is a lot like single variable calculus. You just do it multiple times. Well, let's begin. So, what's our plan? When we're looking for a total, break things into small parts, get a good approximation for each part, and of course, what does that mean? Well, the idea of when you break things into small parts says, hey, each part is behaving like something which is flat. And the way we should interpret flat is something where it's easy to get a very good estimate for. And then we put them all back together, and life is good. Now, the cool thing about calculus is, hey, really good local approximations for small pieces, when you add them up, become great approximations for the totals. And as you make better and better approximations, your total approximation, that is, becomes perfect. That's the beauty of calculus. So, what's the picture to have in mind? Well, when we had a single variable function, y is a function of x, and we were after understanding, okay, what's going on? Well, what we would do is we said, well, split your domain up into little tiny pieces. So, for instance, a little tiny strip, this is, we'll call it a delta xi, and then we had a height. And so we had little tiny rectangles. Now that we're going up to two variables, because we'll start in two variables first, what goes on? Well, it's a similar process. So we have our domain underneath. So here's our domain down below, and that's essentially the equivalent of what was happening over here. Now we're going from A to B. Now what we want to do is we want to split up our domain into easy to digest pieces. So what we'll think of a typical domain piece as looking like is a little tiny rectangle. So that you have a change in your x, your delta xi, and a change in your y, delta yi. So that's your base of your rectangle. And then, of course, there's the height as well. And so we go up and to our function. So we can approximate what's happening with a box. So the total contribution from that piece we think of as being a box. There's the height, which you come from plugging the function in. Then there's base is length times width. Change in x, change in y. So we usually think of that as delta A, the change in area. All right, so if this feels familiar, that's good. It should feel familiar. It should feel an awful lot like what we were doing before, breaking things into parts and adding them together. And we see that we're going to have a lot of the same properties. Now, this breaking things apart and adding them together, that's what we call Riemann sums. And remember, how does it work? Well, just break things into small parts, and for better approximation, make them smaller. And so we say, hey, if, as the way we break things into parts, our pieces get small, and small in the sense that both in the length and the width. So in other words, I don't want a long, skinny piece. I really want little teeny tiny pieces. And the reason I want little teeny tiny pieces is that they do a better job of keeping the function behaving more like a constant. So as my parts get small, I look at what happens to the sum. When the sum exists, we say it's integrable, and we indicate it using this notation. Now, one thing I want to point out is we're going to try to do this very consistently, is you count the number of integral signs. Notice there's two integral signs. Now, when you see two integral signs, what that means is that it's a two-dimensional integral. In other words, what you're integrating over is something which is two-dimensional. So when you see one integral sign, that's a one-dimensional integral. Two integral signs, that's a two-dimensional integral. 3, yes, we'll get there, three-dimensional. When you see like 10, that's 10-dimensional, but usually by that time we have better notation than that. When will things be integrable? In other words, we said, well, if this limit exists, okay, then we can do it. Does it always exist? And the answer is no, not always. But if we have nice functions, and all the functions we'll see are nice, examples of nice functions are continuous. So if we're continuous over our interval, good, easy to do. Some really basic facts. These are all fairly easy to convince ourselves of. So for instance, if we integrate 1 over our region, that's the area. Now, why would that be true? Well, if you think about what we're after, when we think about integrating 1, it says, look, when we break this up into pieces, what's the contribution from each piece? Well, the contribution from each piece is your little change in x, your little change in y, and times 1. So in other words, the contribution from each piece is the area of the piece. So when you add up the little parts, you get the area. So, all right, and that's it. That's the argument. So, great. We can integrate 1. Woohoo! Nice. We can also integrate 0, by the way. Okay, good. Of course, we want to do more interesting integrals. We can pull out constants. So if I have a constant, I can pull it out. And we can break up over addition. Now, if you combine these two, in other words, pulling out constants and breaking up over addition, this is just a very fancy way of saying that integration is what we call linear. And in other words, it gets along well with pulling out constants and addition, but that's because we're really basing integration off of adding. That's the basis of integration. And because adding is nice, it doesn't matter what order we add things in, and we can pull constants out when we have everything multiplied by the same amount, then we can do it with integration. So a good rule of thumb is pretty much anything you'd expect to be able to do with addition, you should be able to do with integration. We can also do comparisons. If one function is below another function over our region, then the integral of the function is less than or equal to the integral of the other function. And you can think of the picture. What is this trying to say? Because, well, how do we interpret it? If we think of things in terms of, say, volume, that's not a bad way to start building up intuition. Not every integral has to represent something geometrical, but it's not a bad way to start. So what happens is, okay, you have your region R down here, and then what you have is you have your lower function, which is f, and that's sitting here over R. So there we have our function sitting over R. Here's our f. And then on top of that, we say, okay, above that is another function going up a little bit, and that's our function, that's g. And they don't have to look necessarily the same, they could look very different. But the point here is when you look, whenever we break things up, the height for f is below the height we can pick for g. And therefore, for each piece, we can say, look, piece by piece, I can bound the Riemann sum of the one for f below the one for g, and therefore, it's always going to have that relationship. The inequality is maintained. Now, the last thing says, look, I can also break my region up into pieces. So imagine that I have, say, our region, think of it as a big rectangle. I can break it into two smaller rectangles side by side. That says the integral over the region, f of xy, is the same as the integral over the smaller region and the other smaller region, region 1 and region 2. And you can break things up into pieces, and this is perfectly allowed. The only rule is it says, look, when regions overlap, they can only overlap on the edges. Because you'll notice, you might say, wait, something seems wrong with our picture. Look, aren't you like double counting the place where they come together? And the reason that we're okay is if you think about where they come together, it's a one-dimensional thing. and we're really doing a two-dimensional integral. And so when it comes down to it, a one-dimensional object has no area, and so it won't affect the answer. It's a lower dimensional object. It's the same thing as, oh, you go from A to B, and then you go from B to C. It's the same as going from A to C. You know, the fact that B showed up at both, that's perfectly fine. Didn't change anything. So why do you want to do this? Well, one reason you might do is you say, hey, I have a function where it's a piecewise function. So in one part it has one definition, another part has a different definition. All right, split them into the parts so you can think of them saying, okay, at each part, it's just a single kind of behavior. So it's useful for breaking up piecewise functions. We'll also see that the idea of breaking an integral into region comes into play when we start getting to more interesting shapes. Yes, we can do things other than just rectangles. That's to come, but that's for a different session. For now, we're just saying, okay, let's start with our basics. Okay, so we can at least talk about integration, but it sounds like it's going to be tricky. How do you actually do it? Because at the end of the day, we want to be able to integrate. And this idea of like, well, we'll break things into little teeny rectangles and add things up, it intuitively wonderful, great idea. But in practice, how do we do it? How do we make it work? So we're going to switch. So instead of saying, let's break things into small parts, we say, no, that's not what we want to do. What we're going to do is we're going to say, let's break things into strips. So think of it as you have this three-dimensional thing. You have your region down here. There's this surface, z equals f of xy up here. And now, instead of breaking it into lots of little tiny pieces, you're going to do some slicing. Slice, 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 slice. So how can you slice? Well, there's a couple of different ways. One way we could slice is we could say, well, suppose we held y fixed. So if we held y fixed, the picture that would be coming out our slice would be this piece right here. So in other words, what you see coming out from here is this piece in the plane. Now, you might say, well, wait, don't you need a little bit of thickness? Yeah, there is a little bit of thickness. We'll come into that in a second here. What's the contribution from the slice? Well, I can say, if I think of the area of this slice, that's the integral from a to b, f of xy dx. Now, keep in mind, this is going to have y at the end. So there's still going to be a function of y involved here. That's perfectly fine. That's perfectly fine because we want the area can vary with y. So now we say, okay, well, what's our volume? Well, we're adding up the area times change in y. Okay, well, what's the area? Well, it's the integral a to b f of xy dx. So we're adding up this integral. Well, adding up is really just integration. So you get the integral from where to where? Well, from c to d, great, of the integral a to b f of xy dx dy. Okay, now, so that says if we slice where we hold y fixed, and then see what happens. But look, that's not the only slice we can do. We can look at other slices. So let's do a slightly different slice. All right, suppose we do x fixed. So if x is fixed, what's our picture look like? Well, it's this slice here. That's the slice we're pulling out. See, because x fixed, I'm coming along here, x doesn't change. So we say, okay, great. So what we see is our cross-section. We get a nice little thing. We say, okay, x is a fixed value, so I can think of it, well, okay, what's the area for that value for x? Well, you integrate c to d f of xy dy, because look, you go from c to d. That's the bounds. And then you have this height, f of xy. And yes, it is a function of x, but that's perfectly fine. So our volume, adding up our area, and it becomes adding up the integral, delta x. Say, well, great, no problem. As we take smaller and smaller slices. In other words, thinner slices, our sum becomes an integral. So we say, beautiful. What is this saying? It really says, how do you go about integrating? It's very straightforward in some sense. It says, do it one layer at a time. Or put another way, we call this iterated integrals. So just means we do it one layer at a time. Work from the inside out. So do the inside layer, then do the outside layer. And when you're integrating, remember, you're only integrating with respect to one variable. Treat the others as constant. So you have to pay attention. What's the variable I'm integrating with respect to? Now, what does that mean? It means that all those times when your calculus teacher said, it's really important, please, 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 please pay attention. Please make sure you don't lose anything, because someday you're going to want to make sure you have good notation. This is the day. They knew you were going to be here, and they knew that you needed to remember that notation will tell you what to do. So what do we mean by notation is important? Well, what we have is the order that things happen tell you the order to do things. So you always work from the inside out. So the inner layer is with the x. Then the next layer is with the y. And so when we talk about this integral, see, the inner layer goes, the inner dx goes with the inner integral. So this says, oh, this is x equals a, x equals b. So x equals a, x equals b. Then the next layer, well, look, that's associated with the y. Y equals c to y equals d. So pay attention to notation. It's really, really important. And that's why you want to make sure you understand what's going on. And this is going to, a nice idea that's coming up says, hey, you can switch the order that you choose to integrate things in. And that's why you have to pay attention. Well, what's the current order I'm actually integrating things in, so I know how to talk about switching. So, in fact, well, here we are. If you have a rectangle, x goes from a to b, y goes from c to d, our conclusion is, if I want to integrate over that rectangle, my function dA, well, I can integrate either first with respect to y, then with respect to x, or first with respect to x and then with respect to y. So, what's that? It says, look, we get to make a decision. Which order do we want to integrate with respect to? But we have to make sure we're set up for it. Now, I want to put a big, be careful here. So here we go. Be careful. Look how big this be careful is. I was like, wow, this is like super big. You might look at this and say, oh, it's super easy to change the order of integration. No! It's super easy if we have a very nice region. And rectangles are nice. So it's a very simple thing to change the order of integration for rectangles. Not so simple when we get to more interesting regions. We're going to have like a couple of sessions where we're going to do practice, 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 where we talk about setting up and changing order of integration. One important thing is changing the order of integration won't change the answer, which is good, because if you think about what's happening, when we talk about an integral, it's finding a total. So when we talk about changing the order of integration, it says, hey, let's talk about finding the total in a different way. And so it shouldn't matter how you find the total. It doesn't affect what the total is. It'll still be the same value. So keep that in mind. Now, at that point, you say, well, why would we bother? And here's the nice thing. Sometimes, if you change the order of integration, the problem becomes simpler. And sometimes, it becomes possible. Yeah, if you change the order of integration, you might have an integral that, look, I can't make any progress with the integral as it currently is, but if I switch the order, I can make progress. And so that's why, keep that in mind. It's a nice tool to have in your pocket. says, okay, should I think about changing the order in which I integrate things? And remember our mantra, we will do that if it makes things easier, because that's what we want. Our goal is always to say, can we make things easier? Because we want things to be easy. That means we're more likely to succeed. All right. So we will get lots of practice, by the way, with changing order of integration. If you're not convinced yet, do the practice. You're going to be like, well, okay, the practice convinces me. Practice is really important. Now, there is a sometimes useful fact, and I will do this from time to time. When you have a function, which is a nice function, in the following sense. So our function, which depends on x and y, is really a function of x times a function of y. In other words, I can sort of separate. They're multiplying together. And if we're integrating over a rectangle, so how do you know if you're integrating over a rectangle? Well, essentially, you know if you're integrating over a rectangle if your bounds are numbers. So if your bounds are numbers, rectangle. That's how you should think of it. If that's the case, then there's this beautiful fact. And it says what? Look at the integral. Suppose you have this integral. Let's look at the inside, because we always go from the inside out. When we look at this integral, what do you see? Well, we're integrating with respect to y. How do we know that? Because it says dy. So we know we're integrating with respect to y. How do we think of this function of x? The answer is it's a constant when we think of it with respect to y. So since it's a function of x, I can pull it out. Aha! Cool. So that's what we did. To go from there to there, it says, oh, pull out the constant. Now, what's happened? Well, look at this integral on the inside. What do you see? Well, what you see is it's a number. You're integrating from a value to a value, a function of one variable, d that variable. So since it's a constant, you can pull it out. So I can pull it out to the front. In this case, I'll pull it out to the back. Doesn't really matter. And so we have the constant came out. There's our constant again. And then there's the other piece. And so we say, aha, what's the punchline? If your function is a product of single variable functions and you're integrating over a rectangle, it says, okay, just integrate, the first piece over, the bounds, the second piece over the bounds, so forth and so on. So you can really separate, and it turns the multivariable integration problem into a product of single variable integration problems. But just a word of warning, be careful, be careful. You do not have to do this. If you're not comfortable, don't do this. And you have to keep in mind, it doesn't apply. In all cases, there are certain functions which this doesn't work. As a very simple example, if you have a function e to the x times y up here, you cannot write this as a function of x times a function of y. It just can't be pulled apart. And so this does have a lot of limitations. You have to be over a rectangle. You have to be able to write your function as a product. It will turn out that a lot of our examples show up to have that format, and so this is just a shortcut, but only use it if you feel comfortable with it. If you don't feel comfortable with it, it's okay not to use it. All right, well, let's go out and do some integration. Time for practice.